For the past few weeks, we've been discussing images, how to find them, where they're located, their properties, and we've been discussing them in terms of a flat mirror. So if I have an object like this, light from a room is going to come off at some angle and cause this object to reflect some incident ray that's going to do something like this, or something like this. And according to the law of reflection, we know that the angle of incidence is going to equal the angle of reflection. The angle of reflection. This is nothing new. We also kind of understand the fact that I have to trace all of these rays back, and they will be traced back eventually to a single point that we call the image. Hopefully this should be review. It should also be review that the distance from the object to the mirror, this distance right here, is identical to the distance from this image to the mirror. Now remember, this image is a virtual image, and the reason it's virtual is because it is behind the mirror system. In future videos, we'll talk about real images and how they're in front of the mirror, but right now this is a virtual image. Well, that's all fine and dandy with a single plane mirror. But what if I had more than one mirror? In fact, what if those mirrors were at right angles to each other? What if they were at right angles? So let me go down here and draw a mirror system with two mirrors that are at right angles to each other. And we're still going to have an object. We're still going to have this object right here. And what if I imposed the question, how many images would you expect to see? And I encourage you to pause the video to think about that question. How many images would you see with two mirrors? Okay, well, to start out, I'm going to draw this. I'm going to draw two rays. I'm going to draw the first one going somewhere like that, and the second ray doing something like that. And of course, we know that according to the law of reflection, each of these rays, we're going to draw the normal line, which is perpendicular to the surface of reflection. And I'm going to draw this ray right here. Now, you understand that the story is not complete here. And I'm going to draw that just a little better. Oops. I'm going to draw that just a little better because, oh, no, don't say that. Draw it just a little better. Sorry about that. Guess I have to erase it. First time doing a video like this. Give me some slack. All right, so that wasn't too much better, but you understand the picture. So you also understand that this reflected ray is going to be bounced off again to this mirror. We'll get to that in just a minute. But understand that angle of incidence equals angle of reflection. Well, you still have to trace this back, just like all images. We're going to trace that back. Now this ray right here is also going to be compared to the normal line. And it's also going to come out at an angle that's going to look something like this. And we're going to trace it back to this location. And this location right here is an image. Well, that's all fine if you are sighting, if your line of sight, if your line of sight is right here. This is my eye. It's a very bad eye. But if your eye is sighting along this path right here, along this path, then you can actually see the image, this specific image. But let's say that, I'll do this in a different color. Let's say that instead, oh, I don't know, we're going to do two rays that look like this. Actually, make it just a little better. Okay, one of them is going to look like this. The other one's going to look like this. All right, well, the law of reflection is still going to apply, so I'm going to do this one first, draw the normal line. And the angle of reflection is going to be like this. and we're going to trace it back to a point over here. Now, this law of reflection is going to do something like this. But you know that this ray, just like one of the red ones, is also going to bounce off. Again, I'll get to that in just a minute. But for right now, we trace this back until everything diverges. Now, the word diverge means that everything goes out in different directions. And what I mean by that is if you look at these arrowheads right here, so I'll go and highlight that. If you look at these arrowheads right here, notice that it starts out from this point right here and it is going off in so many different directions. And you have to pay attention and you have to draw your arrowheads correctly because the opposite of diverge is converge. And converge means that all the light rays are coming in to a single point. And drawing all these reflected rays and tracing them back to a single point might seem like everything's convergent, but you just have to remember that the arrowheads are going in the other direction. So don't get confused by that. Everything is diverging from that point. Okay, so we have a second image that I'm going to label as our second image. This is pretty cool so far. We have two images just like you'd expect. But here's the thing. These are called primary images. They're called primary images. I'll label that right here. This is a primary image. And it's called a primary image because we only traced back the ray after it bounced off the mirror one time. Primary kind of is associated with the number 1, just like secondary is 2, tertiary is 3, and so on. These are both primary images because if you trace the ray, like this one right here, follow the cursor, it bounced off once and we traced that. Right here, it bounced off once and we traced that back to an image. We're going to talk secondary images, and this is where the cool stuff comes in. This is where the unexpected suddenly appears. What if I take these rays and I extend them? So remember when I said that this ray is going to reflect off the mirror, and you would expect it to reflect again. So I'm going to go ahead and show that. So I'm going to show another normal line right here. And because of this angle right here, we're going to make this angle just a bit bigger. And now it leaves the mirror system. However, because I drew a reflected ray, we have to trace that back for our image. So I'm going to trace that back. And I'm going to do the same thing with one of these green ones. So this green one is coming in, and I'm going to draw a normal line like this. Hopefully you can follow all the colors. It's going to go out at this angle. At this angle. And if we trace that back, if we go all the way back, we're going to find something cool. We're going to find that these mirrors are eventually going to intersect at a third point. And this is technically an image. Now, I don't have mirrors with me, so I can't really show you this. However, if you have mirrors at home, or maybe Mrs. Durham has some and you can play around with those, hold 2 mirrors up at 90-degree angles, you will see 3 images. And it's based off of the principle of secondary images. So this is a secondary image because the rays that we traced back were rays that struck the mirror a second time. So this is important. It's a secondary image. So for this right angle system, we have an object, and if your line of sight is right here, then you see this image right here. If your line of sight was this, you would see this image. But if your line of sight was a little obscure and you were looking at the corner, if you were looking at this crease right here, you would actually go all the way and you could take a look at this image. That's pretty cool. Now, I'm going to show you something else that's pretty cool about a right angle mirror system. So this secondary image, you would expect it to have similar properties to the other images that we've studied, and thus is the case. Thus is the case. So, I know I have all this stuff right here, but I'm going to try to highlight. this distance from the object, which is right here, the distance from the object to the mirror is identical, it is identical to the distance to the image. This distance is identical to this distance. Okay, this distance is also identical to the distance to the image. And just like you would expect, the distance from the object to the crease of the mirror, this object distance is always identical. Maybe not in my picture because I'm a horrible drawer, but it is always going to be theoretically identical to the image distance. This and this are the same exact distance. Now I'm going to share one more characteristic. Now, a secondary image, you're going to have all the same characteristics, so it's going to be the same size, the same shape, nothing changes except it's upright, but there is no left-right reversal. If you look at yourself in a mirror and you're raising your left hand, the image in your mirror appears that you're raising your right hand. But a secondary image actually shows you what you are physically doing. So you could be raising your hand, your left hand in a mirror, and these two images right here, so the one that this eye is looking at and the one that this eye is looking at right here. So these two eyes are going to see the opposite hand being raised. However, this eye is going to see your left hand being raised. If you raise your left hand, it'll see your left hand. Vice versa, if you raise your right hand, these will say that your right hand, or I'm sorry, that your left hand is being raised. But if you're raising your right hand, this says, hey, you're just raising your right hand. So it's kind of an opposite because if you think about it, all of these rays are coming in and they're being bounced off a second time. So that's kind of why everything gets flipped again. Okay, so that is a right angle mirror system. In the next video, I hope to explain other mirror systems and to kind of use this as a framework to build on things like 30 degrees or 60 degrees or what happens if the angle is not 90. I hope that was helpful and see you in the next video.